All right, we started molarity in class, and molarity, what it is a unit of concentration. When we're doing chemistry, we need a medium in which the chemicals can actually get together, and typically that will be done for us in this class in aqueous phase. So molarity is a unit of concentration. What does that mean? So I'm just going to try my best to draw a container, and let's say this container is a 1 liter container. So this is a liter of volume, and I'm going to put into that some solute particles. So I'll put a few in here, and let's just say each one of these solute particles represents a mole of particles. So molarity, it just tells us in this 1 liter container what is the concentration of the particles in that solution. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9 particles in that solution. We're going to call each of those particles a mole of particles. So that would be 9 moles of particles in 1 liter, and we would designate that as a 9 molar solution. What does that mean? That means 9 moles of particles of whatever we're talking about in every 1 liter of solution volume. I'll just abbreviate solution here because you don't really want to tough out my handwriting, which is dreadful when I'm writing on this pad. But here we go. So chemists use the term concentration to designate the amount of solute dissolved in a given quantity of solvent or solution. The greater the amount of solute dissolved in a certain amount of solvent, the more concentrated the solution. Guys, that's just like another derived unit, which you're familiar with, might be miles per hour. So if you're going 60 miles per hour, versus 80 miles per hour, if you're out on Texas 130 or you're going 85 miles per hour, you're going a lot faster. That means the numerator is a larger value, but the denominator is still 1 hour. All right, so here we go. So that's going to be our constant for the denominator when we're talking about molarity. It'll be 1 liter of solution. All right, so molarity, moles of solute divided by liters of solution. You need to remember what this is because we can use this as a conversion factor. If we have volume, we can convert to moles using this. If we have moles, we can convert to volume using the molarity. We might represent it as a capital M divided by or capital M, which means molarity, which is moles over capital L, liters, or even N, which stands for moles as well. That's just another way we designate moles, and the volume is in liters of solution. All right, so here we go. So molarity, like density, can be used as a conversion factor to change between volume and number of moles. If you have the mass of a solvent, remember to convert it to moles of solute using the molar mass, and we're going to divide by the molar mass. So here's our first example problem, which I'll do for you. You have 11.5 grams of a solid, sodium hydroxide, which is very soluble in water. Okay, so if we're going to convert this to moles per liter, which is molarity, just assume that's molarity. We need moles, and then we're going to divide by liters, okay? And we've got 1.5 liters of solution. They did a lot of the work for you. All right, so here we go. So the first thing we need moles. And that's going to be 11.5 grams of sodium hydroxide. And the molar mass of sodium hydroxide is 40 grams per mole. That's kind of handy, easy to remember. Okay, the grams cancel, and when I do the math, okay, that gives me 11.5 divided by 40 That gives me 0.288 moles to 3 sig figs. So that's going to be 0.288 moles. Now, all I need to do, believe it or not, that is an 8. All I need to do to get molarity is divide by 1.50 liters of solution. So I'm just going to put my 1.50 liters down here and do the division. So I'll divide by 1.5, and that gives me 0.192 capital M, which is our symbol for molarity. Now, ordinarily, when I'm calculating a molarity, I would just do 11.5 grams divided by 40.00 grams per mole, and then I would divide by, if I have it, liters of solution. And I just put it in my calculator, 11.5 divided by 40 divided by 1.5, and you will get the same answer. All right, your turn. So number 2 that you're supposed to do is a little bit different, but what I'm going to do is I'm going to show you how to use molarity as a conversion factor. So this is going to be a little bit of dimensional analysis. It says how many moles of sodium chloride are in a 355 milliliter sample of a 2.50 molar sodium chloride solution. So the how many moles, which is just X moles of NaCl, you set it equal, and then you're going to put your volume in next. Now I need you to remember that volume times molarity, and keep in mind that molarity is moles over liters, is equal to moles. Why? Because the volume in liters will cancel and I'll wind up with moles. So here we go. So my volume is 355 milliliters. I'm going to go ahead and convert milliliters to liters. How do I do that? I divide by 1,000 milliliters, which are equal to 1 liter. Okay, so now what's happened is milliliters have canceled. I have my volume, and now all I have to do is multiply times my molarity. I have 1 liter down here, and then 2.50 moles, because molarity is equal to moles over liters. So when I multiply and divide, the liters cancel, and I wind up with moles. And so my answer that I get here is going to be 355 divided by 1,000, which is just 0.355 times 2.5, which gives me 0.888 to 3 sig figs, 0.888 moles. Well, that worked out kind of nice. Okay, so there you go. Let's see how many grams of sodium carbonate are needed to make 115 milliliter of 0.5 molar sodium carbonate. All right, so why don't we do this one as well? So remember, the how many part, that's your X factor, that's what you're looking for. And so it's X grams of sodium carbonate, there's the formula right there, Na2CO3. You set your equal sign, and we've got 115 milliliters of a 0.5 molar solution. So what are we going to put on the other side of the equal sign? We're going to put the volume, because again, we're going to multiply volume times molarity to get to moles, and then we're going to multiply moles times the molar mass in order to get grams. So once again, we're going to divide by 1,000 milliliters per liter. Now comes my molarity. My 1 liter of solution has 0.500 moles. That's what 0.500 molar means, moles over liters of solution. And then finally, I've got 1 mole of sodium carbonate, this stuff right here, and they give us the molar mass. They made life easy for us, so we're just going to plug that in. We're multiplying moles times the molar mass. So that's 105.99 grams. I really am doing the best I can here, guys. All right, so milliliters cancels, liters cancels, moles cancels, and we wind up with grams. So let's see what we get. 115 divided by 1,000 times 0.5 times 105.99. And I get 6.09 grams. Now, you can always check this out, okay? 6.09 grams. You could always check this out by simply dividing this by the molar mass, 105.99 grams, and that's grams per mole, sorry. And then divide by liters of solution. 115 milliliters divided by 1,000 is 0.115 liters. So we'll do that. 0.115 liters. And that should give us a 0.5 molar solution. All right, let's read here. As we have seen in many aqueous reactions, not all the ions react. Some of the ions remain in solution as spectator ions. You're familiar with those guys. Therefore, it's also important to be able to determine the molarity of specific ions in solution. So let's go ahead and do that. Now, this is actually very simple. So if I've got calcium chloride, you can see then, if I look at my specific solubility rules, all chlorides are soluble except for silver, lead, and mercury. This is going to be a strong electrolyte in good old H2O. It's going to dissociate into calcium 2+ ions in aqueous solution, plus you're going to get 2 chlorides for every 1 calcium ion that dissociates in solution. So that's not Cl2, that's 2 discrete chloride ions running around. It's just a 1-to-2 ratio. So if the concentration in moles per liter of calcium chloride is 2.5 molar, then your concentration of calcium ions is also 2.5 molar. But take a look, you've got twice as many chloride ions, so that's going to be 2 times 2.5 molar, and oh my goodness, 2.5 mole, that is just dreadful. I can't live with that. I don't know about you, but I can't live with that. So that's going to be 2 times, wish me luck, 2.5 molar, or a 5 molar solution of chloride ions. So I have 5 molar of chloride ions because I have 2 chloride ions for every 1 calcium ion, and I have 2.5 molar for the calcium 2+ ions. All right, let's take a look at this other example. It's a little bit more challenging. Let me go ahead and roll up on it a little bit, get it more in the middle. All right, what is the molar concentration of each ion if you've got 0.22 moles of aluminum chloride dissolved in 0.5 liter solution? Well, the first step is to go ahead and solve for the concentration of aluminum chloride. So here is aluminum chloride. We have, I'll go ahead and put it, you have 0.22 0.220 moles of aluminum chloride, and I'm going to dissolve by 0.500 liters, and it looks like we're just going to we're going to have double the concentration, or double. So that's just going to give us 0.44. Okay, so we're going to have 0.440 molar concentration, this is moles per liter concentration, of aluminum chloride. Now, all chlorides are soluble except for silver, lead, and mercury, so let's take aluminum chloride. And I think you know what's going to happen. We're going to put it in water. It's going to dissociate into one aluminum ion, which has a 3+ charge, and 3 chloride ions in aqueous solution. So if our concentration of aluminum chloride is 0.440 molar, then our concentration of aluminum is 0.440 molar, and our concentration of chloride ions is 3 times that. So it'll be 3 times 0.440 molar. Our concentration of chloride ions will be 1.32 molar. So this will be 1.32 molar in chloride ion. Now, it might be that they ask you for the total ionic concentration. That is the concentration of all the ions in solution. So all you would do to obtain that is to go ahead and add the concentration of aluminum ions here. Okay, this is 0.44 molar. Okay, so I'm just going to add that to 0.44. Too many. And that gives me 1.76 molar. So I now have a 1.76 molar concentration of all ions in solution. So we call that the total ionic concentration. Okay, total ionic concentration. Okay, let's talk about dilutions. And in a dilution, you have a solution of some known concentration. It's usually very concentrated. That's the way we get the solutions from the manufacturer. They're always concentrated because that means you have less volume. Less volume means less mass, and less mass means it's cheaper to transport. But you probably don't want to use a concentrated solution in your laboratory. You may have a need for something much less concentrated. And so you can take a known concentration and you can dilute it. Basically, you're just adding solvent to spread out the concentration of moles of your solute. It just becomes less concentrated. I've worked in places back in the old days where you didn't have a Keurig coffee maker. You had some Mr. Coffee back there, and you know it's late in the day, you're a little bit tired, you need a jolt of some Java, some good coffee, but you go back and the Mr. Coffee has this gooey layer of coffee sitting on the bottom, and you're not going to drink that. So what you do, if you don't want to make a whole pot of coffee, is you put some more water in it, and you put some water in it, you dilute it, make it less concentrated, stick it in the microwave, and heat it up. Now, it tastes just absolutely awful, but it's better than drinking the goo that was sitting down the bottom because all the water had evaporated out. All right, so terrible example. Note that the number of moles of solute does not change when the solvent is added to the solution, just like my gooey coffee here. When I added water, the volume increased, the concentration decreased, but the number of moles of actual coffee stayed the same. So moles before, okay, the dilution equals moles after the dilution. What we have here is we have a high concentration, a low volume on the initial side, and then on the final side we have a low concentration and a high volume. And you remember that volume times molarity equals moles. So higher volume times lower molarity equals the same number of moles that a lower volume times a higher molarity will give you. I don't see what I want to, so here's the way I normally think of it is M1 V1 equals M2 V2. So sorry, that looks like a broken M, but you're used to it by now. So at any rate, remember, this is the high concentration and this is the low volume. Over here you have the low concentration and the high volume. All right, so here we go. What is the molarity of a solution? I'm going to kind of move this up a little bit. What is the molarity of a solution of sodium hydroxide formed by diluting 125 mils of 3 molar solution to 500 mils? So here's the deal. So we need M1 V1, oh that's not bad, equals M2 V2. So what is the molarity of a solution by diluting? Here's my 3 molar, because it's telling me I'm diluting this. So this is my higher concentration. I can tell that because I've got over here 125 milliliters of volume. That's 125 milliliters. And over here on the M2 side, I'm looking for my new concentration, but my new volume is the higher volume. That'll be 500 milliliters. So here we go. Once again, handwriting is spectacular this evening. Okay, it's Saturday night. What are you doing? 3 times 125. And what do I need to do? It looks like what I need to do is simply divide by 500 milliliters. Okay, it'll cancel over here. So I'm going to do the same thing to this side, 500 milliliters. And milliliters cancel. So that's 3 times 125 divided by 500, which gives me 0.75 molar. So M2, my lower concentration, is 0.75 molar. Okay, that would be my answer there. Now, some people might ask, well, you're in milliliters. Don't I have to convert to liters? Well, if one of these was liters and one was milliliters, you would need to convert one of them to get them to be the same unit of volume. But because they're both milliliters, for instance, if I wanted to convert both of these to 1,000, I'd have to divide both of them by 1,000. That's 2 extra steps. Why do that? Because the milliliters, the volume is going to cancel, so it won't make any difference. Okay? Just remember that M1 V1 equals M2 V2. You have the high concentration, you have the low volume, you have the low concentration times the high volume. And number of moles equals the same on both sides. All right, your turn. I want to go ahead and remind you that the dilution equation is what you do when you're dealing with a single substance that you're diluting. We are going to do problems in just a little bit that are called titrations, and that's very, very different. Okay, let's do part 4, which is solution stoichiometry. Remember that moles of a substance is the central component of any stoichiometry problem. The moles of a substance in a solution is determined from the molarity equation. So take a look. Here's where we are. Molarity is moles over volume. N equals moles. This is volume, okay, and volume in liters. And if we want to rearrange the equation, we can solve for moles. And moles is equal to volume times the molarity. How do we see that? Here's your volume, here's your molarity, which is moles over liters. The liters cancel, and that gives you moles. That's what's left over. So if you have concentrations of one substance, you have to convert to moles first. Everything goes through moles, guys. We use the mole-to-mole ratio from the balanced chemical reaction in order to do this. All right, so I'm going to pull this up a little bit. Here we go. I know this has been going on for a while, but oh well. Here we are. Given that 37.5 milliliters of a 0.1 molar aluminum bromide. So here's aluminum bromide, 37.5 milliliters of the stuff. We've got a 0.100 molar solution of the aluminum bromide. It reacts with silver nitrate. What is the mass of silver bromide? Now here's the deal. We're assuming we have an excess of this. This is just like the stoichiometry problems that we were doing before, only we're starting with a volume, and volume times molarity equals moles. And then what we're looking for ultimately is X grams. So it's very similar to gram stoichiometry, except that we're not starting with grams, we're starting with volume. Remember, with grams, we converted grams to moles by dividing by the molar mass. Well, here we're converting volume to moles by multiplying volume times the molarity. All right, so let's get started. So this is X grams of silver bromide. Why do we know that silver bromide is a precipitate? Because all bromides are soluble except for silver, lead, and mercury. So here we go. All right, I've got 37.5 milliliters. I'm going to go ahead and convert milliliters to liters. How do I do that? I divide by 1,000 milliliters per liter, and then every 1 liter of aluminum bromide is 0.100 moles. It's not capital M. Moles over liters is capital M. That's what molarity means, moles over liters. Now we have the mole-to-mole ratio. So I look at the coefficient of aluminum bromide, which is 1. I look at the coefficient of silver bromide, it's 3. So this will be 3 moles of silver bromide trust me. And then 1 mole of aluminum bromide, which is aluminum Br3. Okay, so where are we? Well, we're, before we were doing grams to moles, mole to mole, and then moles to grams. Well, here we are. We've multiplied volume times molarity. We've converted milliliters to liters, then liters times molarity, which gives us moles. Now the mole-to-mole ratio, and finally, it looks just like gram-to-gram stoichiometry. Every 1 mole of silver bromide, let's see if we can do a little better job on it, It weighs 187.77. 187.77 grams. And there you are. Okay, so milliliters cancels, liters cancels, moles of aluminum bromide cancel. Okay, those guys cancel. Moles of silver bromide cancel. We have grams of silver bromide. We're good to go. So let's go ahead and plug that in the calculator. 37.5 divided by 1,000 times 0.1 times 3 divided by 1 times 187.77 grams. Okay, and that says 2.3 sig figs, 2.11 grams. So there we are, 2.11 grams. Ugh, good Lord. 2.11 grams. All right, and that is silver bromide. All right, so here's the deal. Get yourself into liters, so milliliters to liters, okay, and then times molarity, and then times mole to mole, and then finally moles to grams. Okay? All right, I'm going to leave you to continue working on that, do the rest of it. I'm going to make a separate video for titrations. That's the last thing. This thing has just gone on way too long. All right? See you in a bit.